Hello everyone, welcome to the channel Statistica Hub. So in this video, we'll start with the topic Algebra of Matrices. Algebra of Matrices. Okay. So how the matrix is defined? I have this A matrix which is defined as the corresponding elements of this A matrices are as A11, A12 to A1n. Okay. This is my first row. Okay. And the column A21, A22 to A2n. This is my second row. This is my first row. This is my second row. Okay. Which goes to AM1, AM2 and AMN. And these are my corresponding column. This is my column 1. This is column 2. Okay. And this is column n. So we have this matrix A of m cross n where I have m rows and n columns. Okay. Now there are some types of matrices. Okay. Types of matrices. First is our equal matrices. That when can we say that two matrices are equal? For that, let's say that A is equals to B, where these both matrices are of order m cross n. These both matrices will be equal if I have Aij is equals to Bij, where the matrix A is defined as Aij and matrix B is defined as Bij. Okay, that means we can say that we have equal matrices if the corresponding elements of the matrices are equal. For I is equals to 1, 2 to m and j is equals to 1, 2 to n. Okay, then can we say that these matrices are equal. Okay, now equality relation. This equality relation in the set of all matrices. Equality relation in the set of all matrices. How it is defined? That when can we say that two matrices are equal? That if they follow reflexivity, symmetricity, and transitivity. Reflexivity, symmetricity, and transitivity. What is reflexivity? When my A is equals to A, that A matrix is equals to A matrix. Okay. Symmetricity is when if I have A matrix which is equals to B, then we have B matrix which is also equals to A. Okay. And symmetricity is when I have A matrix which is equals to B and the other matrix which is B that is equals to C. Then I can say that A is equals to C. Then we can say this is transitivity. So for the equal matrices to be equal, these are the properties of relations, equality relations that has to be satisfied, which is reflexivity, symmetricity, and transitivity. Okay. Now let's say diagonal matrices. Diagonal matrices. So a square matrices is said to be diagonal when I have the matrix. Let's say this is my matrix. Okay, where A11, A12 to A1n, and which goes to AN1, AN2 to ANN. Okay, okay. Okay, so this is how I am defining my matrix. Okay, now AII, which means that these elements A11, A22, these are the elements A11, A12, A22 to ANN. That all the diagonal elements, what? All the diagonal elements AII is equal. These are called my diagonal elements for this matrix A11, A22 to ANN. These are my diagonal elements. And the line along which they lie is called the principal diagonal. What? This is principal diagonal. Okay. and diagonal matrix. This is my principal diagonal. These are my diagonal elements, and we say that the matrix is diagonal when ai takes some value, that all the diagonal elements are taking some value and all the other elements, that is aij, are equals to 0 for all I not equals to j. That means my diagonal elements are taking some value and all other elements which are here, these are equals to 0. That all the aij's, that a12, a21, any of them, like here if I can write it as a21, a22, a23, okay, a31 actually. So all these elements are equals to 0. These elements, all these elements are equals to 0. That I have only the diagonal elements and all other than are equals to 0. Then I say that my matrix is diagonal matrix. Okay. So diagonal matrix is aii, which are called diagonal element. And if I have aij which is equals to 0 for all I not equals to j. Okay. Now let's say if I have a matrix of 3 cross 3, which is a11, a12, a13, a21, a22, a23, and similarly a31, a32, a33. Okay. Then what are my diagonal elements? My diagonal elements are a11, a22, and a33. These are my diagonal elements. And for this matrix to be diagonal matrix, I should have all the elements of this a12, a13, a23, a21, a31, a32 as to be 0. Okay, then can we say this is my diagonal matrix. Okay, now there is a term which is called trace. Okay, and this trace is defined as sum of the diagonal elements, the sum of the diagonal elements. That means my trace of this matrix A is equals to A11 plus A22 plus A33. Okay, and let's take a generalization of this. That's if I have a matrix A, then the summation of all the diagonal elements, that is I going from 1 to n. Okay, for an n cross n matrix, then this can be as AII, which is my sum of all the diagonal elements, which are as a11, a22 to an. Okay, now this trace of the matrix follows some properties. Let's see the properties of trace, which are as that trace of alpha a, with where alpha is my scalar. Okay, where alpha is a scalar, then trace of alpha a is equals to alpha trace of a. That means that if I multiply a scalar by a matrix and then take a trace of it is equals to, I take a trace of the matrix and multiply this by a scalar. Okay. Second property is that the trace of A plus B is equals to trace of A plus trace of B. Okay, which means that if I take a sum of two matrices, that if we take a sum of two matrices, then that will be equals to trace of A and trace of B. Okay, and the third property is that trace of multiplication of two matrices AB is equals to the trace of BA. Okay, that if I do the multiplication AB, okay, and that will be equals to the trace of BA. Trace of AB is equals to trace of BA. Okay, now third matrix we have is a square matrix, which is square matrix. So we have a square matrix when we have number of rows. Number of rows are equals to number of columns. Number of columns, which is let's a matrix of A2 cross 2 or 3 cross 3, A4 cross 4. When we have number of rows is equals to number of column, then can we say that we have square matrix. For A of m cross n matrix, if I have m is equals to n, then we say that this is a square matrix. Okay. Now let's come to the scalar matrix. Scalar matrix. Okay. So for a scalar matrix, let's say if I have a matrix A which is defined as Aij, where I comma j are both goes to 1 to n. Okay. And the corresponding elements of this matrix Aij is defined as equals to k for all I is equals to j, that I am writing aii, all the diagonal elements as k, okay, and all the other elements for I not equals to j, if there is a zero, then we say that my matrix is a scalar matrix, okay. If all the diagonal elements, if all the diagonal elements are taking a value which is k, and all the other elements are taking a value 0, then we have a matrix which is a scalar matrix. Similarly, we have unit matrix, which have unit matrix, okay, where let's say A is equals to Aij is a matrix where all the elements, okay, let's say 1, if all the diagonal elements are taking value 1, for all the diagonal elements taking value 1, and all other elements for I not equals to j, if they are taking value 0, then we say that this is my unit matrix or identity matrix, or okay, you can also say as identity matrix, okay, like this 1 0 0 1. This is my identity matrix of 2 cross 2, and scalar matrix is as k 0 0 k. This is a scalar and you can define it as 5 5. You can give any value to the scalar, which is 5 5 4 4, any of this, okay. So this is my scalar matrix and this is my unit matrix, okay. So this delta aj, this is said to be the Kroneker's delta, Kroneker's delta, okay. And if you look to it, that I have this 1 0 and I have this as 0 1 1 0 0 1. The columns of these are 1 0 and 0 1, okay. So I can write these columns as, I can write this matrix as E1, E2, because that's how we have defined EIs, that E1 is 1, comma 0 and E2 is my 0, comma 1. Okay, so we can say that the corresponding columns of this identity matrix are my EI, okay, which are standard basis, okay, and as E1 to En are actually the standard basis of let's say F's power n. Okay, so I can write this matrix of identity by E1, E2 for any 2 cross 2, where E1 and E2 my corresponding 2 cross column vectors. Okay, now there is another matrix, type of matrix, which is said to be the triangular matrix. Triangular matrix. Now in this, let's say I have a matrix of A m cross n, which is defined as Aij. Okay. Now the matrix is the triangular matrix, which is upper triangular. Let's talk about upper triangular. Upper triangular. A matrix is said to be upper triangular if all the elements below diagonal are 0. Okay. If all the elements below diagonal are 0, then we say that my matrix is upper triangular, and you can write it as that if I have Aij which are equals to 0 for if I is greater than j, okay, and I have Aij which is equals to 0 for all I greater than equals to j. So my this matrix is upper triangular as it is taking all the elements below the diagonal elements 0, and this is my strictly upper triangular, strictly upper triangular, because it is taking all the diagonal elements 2 are equals to 0. It has I greater than equals to 0. Okay, so when I have all the elements below the diagonals are 0, then we say that it is upper triangular, and I have with the below diagonal elements 0 and the corresponding diagonal elements are 2 0, then we say that it is my strictly upper triangular. And similarly, if we look to the lower triangular matrix, the lower triangular matrix are actually that if all the elements above diagonal are 0, if all the elements above diagonal are 0, that means if Aij is equals to 0 for I less than j, then we say that it is lower triangular, and Aij is equals to 0 if I less than equals to j. then we say that it is strictly upper triangular, strictly lower triangular. Sorry. Okay. So this is how we can define any a matrix as upper triangular and lower triangular, and strictly upper triangular and strictly lower triangular. Okay. Okay. Now let's see operations of matrices. That how the addition and product of the matrices are defined. Operations of matrices. In the operations of the matrices, let's just talk about the addition first. Okay. So the addition of the two matrices are defined if I have, let's say, matrices of A and B. If I have these A and B of the same order, then the addition of the two matrices is defined. Okay. That means if I have a A of m cross n, then I should have a B of m cross n only. Then I can define its addition as A plus B. Now there are some properties of the additions which are as A plus B is equals to B plus A. That the additions of the two matrices are commutative. Commutative. Second is that A plus B plus C is equals to A plus B plus C. That the addition is also associative. Associative. Okay. And similarly, if we multiply a scalar by the addition of the two matrices, that will be equals to Ka plus Kb. That means it also satisfies the distributive law. Distribution law. Okay. And A plus 0, where 0 is my zero matrix. Here by 0 we mean zero matrix. A zero matrix is basically where all the elements of the matrix are 0. This is a zero matrix of 2 cross 2. Okay. A plus 0 is equals to 0 plus A, and that will be equals to A. That means it signify as the existence of identity. Existence of identity, where 0 is my zero matrix, or you can say null matrix. Null matrix. Okay. And the fifth property is A plus X is equals to 0, then minus A, that X is equals to minus A. Okay. Then X is equals to minus A is the additive inverse. Additive inverse. Okay. You can also see it by the normal calculation that gives some a value which is 1, 2, 0, 1. Okay. And add this matrix by x1, x2, x3, x4, which is equals to 0, 0, 0, 0, 0. And if you find out this x1, x2, x3, x4, and subtract this matrix, which is, we didn't actually subtract, just add this matrix by plus minus 1, 1, 2, 0, 1, and that is equals to my minus 1, minus 2, 0, minus 1, and then I can write it as equals to minus 1 of 1, 2, 0, 1, which is equals to minus 1 of A. Yeah, let's say this matrix is this matrix is A. Okay, so this is satisfied here, that is equals to minus of A. So if I have A plus X equals to 0, then minus of A is the additive inverse of this matrix. So operations of the matrix satisfy commutativity, associativity, distribution law. It satisfy existence of identity and additive inverse. Now let's just see about product of the matrix. Product. Okay. What about the product of the matrices? So for the product of the matrices to be defined, we have number of columns of, let's say, matrix A equals to the number of rows of B. Okay, which is, I am saying that for this matrix A, this is my A matrix, and let's say this is my B matrix. And for this product, which is AB, to be defined, we have number of rows in A should be equals to number of column in B. Oh, sorry, I said it inversely. That I meant to say, if number of columns in A, if number of columns of A are equals to number of rows of A. Okay, these are number of rows actually. Okay, if number of columns of A equals to number of rows of B. Then our matrix product is defined. Okay. So there are some properties for matrix product also, that if I write this as AB, the matrix product, then AB should not be, is always not equals to BA. That is, matrix product are not commutative, not commutative. And if AB is defined, that doesn't mean that BA should also be defined. Okay. And if AB has the matrix this, then it is not always possible that it is equals to BA. Okay. And the second property is that A of BC is equals to ABC. Okay. That is, matrix product is associative. Associative. And third is A of B plus C, which is equals to AB plus AC, that it follows distributivity. It is distributed. Okay. Okay. And we also know that if we multiply an identity matrix by any matrix A, which always gives us matrix A, as these matrix identity are the corresponding EI column vectors, EI column vector, which are our standard basis. So we are actually multiplying the identity matrix by an matrix A. Okay, that would give us matrix A. Okay, which can also be A is equals to identity. These are the matrix product corresponding to identity. Now this matrix product, you can also see this matrix product by the linear transformation topic, that it actually comes from there. We always gain the matrix by the transformation, that there is some transformation from one vector space to another matrix, and then we form the matrix of that transformation with respect to their basis. Okay. So for the matrix product, you can we have, let's say, the transformation goes like V1 to V2, from vector space V1 to vector space V2. Okay, and I have this matrix Aij, which is my matrix of T, matrix of the transformation with respect to X and Y, where my X is X1, Y1, sorry, X1, X2 to Xn, and Y is Y1, Y2 to Yn. Okay, and these are the corresponding bases of vector spaces V1 and V2. This is of V1 and this is of V2. Okay, now if there is a vector X, if there is a vector X which belongs to V1, okay, which belongs to V1. So as this vector belongs to V1 and x1, x2 to xn are the corresponding bases of these vectors, I can write this vector in the linear combinations of these xn vectors. Okay, like x is equals to, for the, let's say, alpha i's which belongs to the field of scalars, I can write this vector as sigma j equals to 1 to n alpha j x j, which belongs to vector space V1. Okay. Now, what will be the image of this vector? The image of this vector is T of x. Okay. And this image belongs to my vector space V2. Okay. So, it means that this image vector which belongs to the vector space V2 and the corresponding bases of this vector space Y are V2 are Y1, Y2 to Yn. So I can write this Tx in the linear combinations of these of these basis vectors of vector space V2. V2. Yes. Okay, so that I can write Tx is equals to sigma I going from 1 to m. Okay. Sorry, this is my m. I have here m. Okay. Sigma I going from 1 to m, sigma j equals to 1 to I, aij alpha j, and this is my yi. So this is the corresponding linear combinations of yi's vectors with respect to yi's basis, and taking into account that I have a matrix A which is matrix of T with respect to the basis of x and y. So by the property of linear transformation, I can write the image vectors in this linear combination like this. Okay. So this linear combination, let's take it here, Tx, which comes out to be sigma I equals to 1 to m and sigma j equals to 1 to n aij alpha j by I. Okay. Now I can write this. I can take this as my beta I. Okay. So that would be beta I by I. So here beta I is actually equals to sigma j equals to 1 to n aij alpha j. Okay. Aij alpha j. And what is my alpha j? So what is my alpha vector actually? Alpha is the corresponding coordinates of the vector x. Okay, the corresponding coordinate vector of the x. So my alpha is alpha 1, alpha 2 to alpha n. Okay, I am writing this in the column vector because we have studied this in the linear transformation, that if I have a vector s and I am representing this in the linear combination of the other vector, then the corresponding coordinate vectors of this vector x are the corresponding columns of the our matrix, columns of the matrix. Okay, so this is my alpha 1, alpha 2 to alpha n. And you can also say that I am writing this in the column vectors because the image of the transformation is equals to the column space. Okay, alpha is equals to the, and if you look to the beta vector, what is my beta vector? Beta vector is what will this give? The result of this vector would be beta 1, beta 2 to beta m. Okay, this is my corresponding beta vector. Okay, so technically we have beta is equals to a alpha. If you look this, where aij are the elements of the matrix A. Okay, so I can write this as beta is equals to a alpha, where alpha are the coordinate vector of x with respect to basis x, and beta are the coordinate vector of tx with respect to basis y. Okay, so what we are doing here is that I have a matrix A. I have a matrix A of the transformation T with respect to basis x and y. Okay, and if there is a alpha, which is the coordinate vector, or you can say coordinate column vector of a coordinate column vector of x with respect to the basis of x. Okay, then a alpha, a alpha, that is the corresponding multiplication of this vector alpha and the matrix A, is the coordinate vector of tx with respect to y. Okay, like this you can just write it simply that A be the matrix of t with respect to basis x and y, and alpha be the coordinate column of x with respect to x, base x. Okay, and a alpha be the coordinate vector of tx, the image of this vector with respect to y. Okay, now in the matrix product, see this also, that for a square matrix, for a square matrix, let's say A. Okay, I have A's power P into A's power Q. Let's take a power of that P when we do the matrix product, which is A into A. That is defined as A square, and similarly A into A, that is defined as A cube. Okay, so if I multiply A by P times, that is my A's power P. Okay, P times that is equals to A's power Q P. Okay, and if we multiply A's power P into A's power Q, that will be equals to A's power P plus Q. And similarly, I have A's power P, and if I take a power of this A's power Q, and that will be equals to A's power PQ. Okay, and we have in the power system that I have A's power P into A's power Q, and that will be equals to A's power Q into A's power P. Okay, from this we got that powers of A of a square matrix commute. That means powers of A commute. Okay, okay. Now there is an important thing which is as defined as division law, or you can say cancellation law, sorry, cancellation law of multiplication. So what is in this law is, for the division and multiplication law, that if x and y, I have this x and y which belong to the field of scalars. Okay, field of scalars. Now x y is equals to 0, that if the multiplication of these two scalars is equals to 0, so from this we got that either x is equals to 0 or y is equals to 0, or we can have both x and y is equals to 0. Okay, but this law does not hold in the case of matrix multiplication. Okay, if we'll do the matrix multiplication, then this law of division and cancellation does not follow in the matrix multiplication. You can see it like this. Let's say if I have this matrix A which is 1 1 1 1 and another matrix B which is 1 minus 1 0 0, then if I do the matrix multiplication of this AB, that will be equals to 0 0 0 0. Okay, and we have, you can see that we have A which is not equals to 0 and B which is also not equals to 0, but the corresponding multiplication of these two matrices are equals to 0. So the cancellation law, that if I have x y, the corresponding multiplication of the two are is equals to 0, then we have x equals to 0, y equals to 0, or either both equals to 0. This does not satisfy in the property of matrix multiplication. Okay. 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 Now let's just see the topic of transpose. Transpose. Okay. In the transpose, I have a matrix, let's say A m cross n, which is defined as A of Aij. Then B is equals to A transpose. That is equals to where A transpose equals to Bij of n cross m. That means if I have this matrix A which is as 1, 2, 4, 5. Okay, then the transpose of this matrix is 1, 2, 4, 5. This means the transpose of any matrix can be founded by if we just take the if we just write the rows of matrix into the column. Okay, like this. I have written this row 1 2 into the first column which is 1 2, and second row which is 4 5 into the second column as 4 5. Okay, and there are some properties of the transpose which is A transpose transpose is equals to A. Okay, and CA transpose, that means the sorry, if we multiply a scalar by a matrix A and we'll just take a transpose of that, then that will be equals to CA transpose, and AB transpose, that is the multiplication of the two matrices and taken the transpose of that, that will be equal to B transpose A transpose. Okay, so these are some basic properties of the transpose. Now let's see symmetric and skew symmetric matrices. Symmetric and skew symmetric matrices. So we have symmetric matrices which are defined as if I have A transpose equals to A. Okay, then we say that my matrix is a symmetric matrix. For A transpose equals to A, I mean that for Aij, the corresponding element of this A matrix, Aij is equals to Aji for all I comma j. Okay, then we say that my matrix is symmetric matrix. Okay, and skew symmetric, for skew symmetric, if we have A transpose equals to minus of A, okay, then we say that we have a skew symmetric matrix which is defined as if I have Aij is equals to minus of Aji for all I comma j. Okay, and in skew symmetric, if we have I is equals to j, that means for the diagonal elements, if we have I is equals to j, that means Aii is equals to minus of Aii, and that can be written as 2Aii equals to 0. Okay, and that will be equals to Aii is equals to 0, and from this we got that every diagonal element of a skew symmetric is necessarily 0. Okay, okay, so skew symmetric and skew symmetric, that's how we can define these matrices. And for this we have studied the zero matrix and identity matrix. If you look through them closely, then my zero matrix is actually the symmetric matrix, and identity matrix is also symmetric matrix. Okay, now there are some properties of these matrices, which are as that I have A and B matrix which are symmetric. I have these two matrices which are symmetric, then the corresponding sum of these two matrices will also be symmetric. Okay, you can see that like this, that I have this A plus B, where A and B are symmetric, that means A transpose is equals to A, and B is symmetric, that means B transpose is equals to B. Then we have to check for A plus B, that means A plus B transpose has to be equals to A plus B for symmetricity. Let's just check that. So A plus B is transposed by the property of transpose. I can write it as A transpose plus B transpose, and that will be equals to A plus B, because I have A transpose is equals to A and B transpose equals to B. Okay, so the corresponding sum also A plus B also follows the property of symmetricity. Okay, similarly AB, the multiplication of the matrices are symmetric if and only if AB is equals to BA, if they commute, if the matrix multiplication is commute. By this you can see that AB's transpose is equals to B transpose A transpose. Okay, and we have B transpose equals to B and A transpose equals to A, so I can write it as BA. And if we have given the condition that if the matrix multiplication of this A and B is symmetric if we have AB is equals to BA. Okay, so by applying this condition, BA is equals to AB, so we got AB transpose equals to AB. Okay, so the matrix multiplication AB is symmetric if and only if they commute, if the matrix multiplication commute. Similarly, third property, which is A transpose and A transpose A, these are symmetric. And if A is a symmetric, if A is symmetric, then KA, that is also symmetric, and AB plus BA, this is also symmetric. You can check these by applying this. That's how we have done for the A plus B's and AB. You can check this by applying this property of A transpose is equals to A. Okay, now we have let's just study first partition matrices first. Partition matrices. Partition matrices. Okay, or you can say block matrices. So let's say I have a matrix A, okay, which is as 2, 4, 3, 1, 0, 1, minus 1, 3, 1, 0, minus 1, 0, 0, 2, 1, 0, 5, minus 2. Okay, and if I want to partition this matrix, then the partitioning of this matrix A into submatrix, into these submatrix, we call these matrices as blocks. Okay, and I can partition this matrices in many ways. Like this is my matrix A, so I can partition this matrix like this. Okay, let's just like this. Okay, and like this too, where we have elements here. Okay, so there are some, sorry, actually there are many possible ways of partitioning any matrix. Okay, so let's just partition this matrix like this, as I have already done like this. Okay, and I can write this matrix like C11, C12, C13, C21, C22, C23. Okay, where C11 is my actually 2 1, C12 is equals to -1, C13 is equals to 0 0 0, C21 is equals to 4 0 3 1, C22 is equals to 3 1, and C23 is equals to -1 0 2 1 -5 -2. Okay, and these are my corresponding elements of the matrix. I am writing this matrix A into this format. Okay, then here I have a matrix of this of 3 cross 6. Okay, and here I have a matrix of 2 cross 3. Okay, so I have partitioned this matrix into small blocks, which is as C11, C12, C13 into these small matrices. Okay. Similarly, let's say I have another matrix B, which is 1 0 0 0 0 1 0 0 1 minus 2 2 5 2 minus 1 2 0 minus 1 3 0 minus 1 0 1 0 0. Okay. So there is the thing to notice here is that just when we have a matrix, then try to get the matrix, the sum matrix. Try to get the sum matrix of this. Like if I have a matrix which has many of the zero elements, then we'll take a the zero matrix, the zero elements matrix into the one sum matrix, because it will help us in the multiplication, addition, or anything. Okay, it will help us in the calculation. If I'll take the matrix of this, if I'll take the if I'll take a if I'll make a different if I'll make a separate sum matrix of this matrix, of this zero matrix. Okay, I'm so sorry about that. Okay, so this is my matrix B, and if I want to partition this matrix, then this can be, let's say I am partitioning this matrix like this. Okay, now this matrix B can be written like D11, D12, D21, D22, D31, D32. Okay, and where the corresponding elements of these D11 is this, D12 is this, D21 is this is D22, and this is D31, and this is D32. And this is also the matrix of 6 cross 4. Okay, and if I want to multiply these two matrices, okay, that is AB. If we want to multiply these two matrices AB, then we don't have to perform these much of long calculations of like multiplying this its first row into its first column and go similarly like that. Okay, we just have to multiply this matrix into this matrix. Okay, that is we are multiplying C11 for AB. We are multiplying C11, C12, C13, C21, C22, C23 into D11, D12, D21, D22 into D31, D32. Okay, I am multiplying this AB like this with the so I will multiply C11 by D11. Okay, so let's just do it like this. First, for this we have C11, C12, C13, C21, C22, C23, and D11, D21, D31, D32, D22, and D11. Okay. So let's just perform first C11, multiply this row into this column. Okay, that's how we perform the matrix multiplication. So when we multiply this, it will give us, it will say that C11 D11 plus C12 D21 plus C13 D31. Okay, and what are the elements in C11? We have 2, 1. In D11 we have 1, 0, 0, 1 plus C12 is minus 1. D21 is 1 minus 2 plus 0, 0, 0, and D31 is 2 minus 1, 0, minus 1, 3, 1, and that will be equals to, let's just multiply them. Okay, 2, 1 plus, this is normal multiply, which is minus 1, minus 2, minus 1 plus 2 plus 0, 0, and this is giving us 1, 3, 1, 3. Okay, so this is my 1, 3 is my first multiplication, which is this is I have to write it like here, which is 1, 3. Okay, let's just perform another one, which is C11 D11, C12 D22 into C1 plus C13 D32. Okay, so it will perform another one, which will give us 2, 1. This is my C11. What is my D1 D12? 0, 0, 0, 0 plus minus 1, 2, 5 plus 0, 0, 0, and this is 2 0 0 minus 1 0 0, and this will give us 0 0 plus minus 2 minus 5, and that is also 0 0. Okay, so this is giving us minus 2 minus 5. So this is the minus 2 minus 5. So minus 2 minus 5. Okay, so now let's multiply this one, C21, C22, C23 by D11, D21, D31. Let's just do it here only. Okay, so that will give us, we are multiplying 4031 by 1001 plus 31 by 1 minus 2 plus minus 10 2 1 minus 5 minus 2 by 2 0 0 minus 1 and 0 0, and this will give us, the first multiplication is 4031 plus this will be 3 minus 6 1 minus 2 plus the third one will be minus 4 12 minus 1 1, and this will be 3. So this is 6 12 minus 6, and this is 3, and 1 minus 1, that will be 0. Okay, minus 2, this is my minus 2. Okay, so I got 3630. This will be 3630, and similarly we'll find for the another one, which is C21, C22, C23 into D12, D22, D32. Okay, and let's just write it here. This will give us 4031. This is my C21, D12 plus 3125 plus minus 1021 5 minus 2 200 0 minus 1 0, and that will be equals to, my first one is 0 0 0 0 plus second one is 6 15 2 5 plus third one is minus 2, that we also minus 2 0, and this is minus 1. Okay, so from here I got this, I got 4 13, and that we see 2, and this is 4. This is 4 13 2 4. Okay, so from the partition of these two matrices, we have just have to perform some small calculations, that we have got the multiplication of these two corresponding matrices, which is A, B, and that will be equals to this. And you can also check it by multiplying the normally, which that we what we used to do, that multiply this first row by this first column. Okay, and the corresponding result is also will be equals to this. Okay, so that's how we can use the partition matrices for the multiplication and for the other purposes. Okay, okay, so for the algebra of the matrices, we will also do some important matrices, which are nilpotent matrices, idempotent matrices, involuntary, unitary, Hermitian, skew Hermitian matrices. So let's just see them in our next lecture. Okay, thank you.